for the two now. Two questions. So number one, at 450 degrees Celsius, 2 moles of H2I2 and HI are combined in a 1 liter container. The value of Kc at this temperature is 50. Is the mixture at equilibrium? If not, which direction will it shift? Oh, I guess we need a balanced equation for this. 1 second. H2 plus I2 at equilibrium with 2HI. There's our balanced equation, right? These are all gases. So there's our balanced equation. We have 2 moles of everything in a 1 liter container. They give us the value of Kc, and they're asking if the mixture is at equilibrium. So remember, if we don't know if it's at equilibrium or not, that's a Q versus K problem. So is it at equilibrium? That tells us solve for Q. Now remember, Q is calculated the exact same way as K is. So if they give us Kc equal to 50, that means we could solve for QC. Again, same way. Products over reactants. You can only have gases and aqueous solutions. So if this is our balanced equation, assume that they gave you this balanced equation as well. So HI squared over H2 times I2. Now, brackets means concentration. It means molarity. Remember that molarity is moles over liters. So if we're solving for Q, 2 moles over 1 liter, that's 2 molar for everything. So let's plug in 2 molar for everything. So HI, 2 molar, that's squared. H2 and I2 are both 2 molar. 2 squared divided by 2 times 2. Well, that's 4 divided by 4. Q is 1. So if we want to know if the mixture is at equilibrium, we compare Q to K. Well, Q is 1, K is 50. So Q, that's a K, is less than K. So to answer the first question, is it at equilibrium? We will say no. It's not at equilibrium because Q is less than K. So if we think about the pictures, so here's Q, here's K. Q is less than K. To get to equilibrium, K is a constant, so K doesn't change. Q is what changes. So Q needs to increase to equal K. For Q to increase, right, this arrow helps tell us which reaction will take place, the forward or the reverse. So this arrow tells us that reactants will produce products. When it says which direction will it shift, it wants to know, are we creating more reactants or are we creating more products? Because we're creating more products, products are to the right of the arrow. So we would say it shifts right to produce more products. Because if we think about it, if we produce more products, that's going to increase the number on top, and it's going to slightly decrease the number on the bottom. So that's going to increase the value of Q. So when something says, is the mixture at equilibrium, that's a Q versus K. K is a constant. We solve for Q. Then number 2, if you're given concentrations at some point in the reaction, that's what happened in number 1. We were given concentrations at some point in a reaction. Explain how we can determine if the mixture is at equilibrium. Well, if we don't know if we're at equilibrium or not, right, that's Q versus K. So I'll just say solve for Q. We solve for Q, that's at any point in the reaction, and we compare it to K. I like using these like bar graphs because that helps us figure out if Q is greater than or less than K, which way will we have to create more of. Yeah.
So do you do the ice tables with the X's when you don't have one of the reactant products?
And that's if you are at equilibrium.
Okay.
Yeah. So you'll use the ice tables if you are looking for equilibrium concentrations and you're not given some piece of information. That's when you'll put in X.
Okay.
Since we don't know if we're at equilibrium here and it just says, here's what you're combining into a container, and they give us K. Now they're not saying what is the equilibrium concentration, it's just asking, is it at equilibrium? So if it's just saying, is it at equilibrium when we put these into a container, that's just Q versus K.
Okay.
Yeah. So you'll notice that a lot of the questions in mastering align to some of the examples that we've done. So I just figured I'd put this on here so that you can see that a lot of the examples matched up. So if you're working on mastering, you're stuck on a question, you can kind of refer to the notes. Remember, in mastering, you will also see converting between KP and KC. So if you have questions while you're working on mastering on that, I was getting some questions yesterday. You can send me like a remind email, anything like that, to ask questions as you're working. All right, so we're going to actually start at the very end of the examples because this is one of the particle diagram questions that we did not get to last week, just because I wanted to give you guys some time to practice and to work. So if you flip in your notes to page 17, so it's the very last sheet of paper in your notes, but it's kind of on the front. The back is the what you need to know. So the very back of the notes, this is what the AP curriculum says you need to know. Well, remember, all of our quizzes and tests are based on the AP curriculum. So if you're like, well, what do I need to review for the quizzes and the tests? Well, just read through this. So this is what you need to be able to do, what you need to know. So for example 25, this says the diagram shows the following reaction at equilibrium in a 2-liter reaction vessel. So I'm going to underline 2 liter because that's the size of the container, right? It tells us right here. Each particle represents 0.02 moles. So last week we talked about how we assume that each particle just represents 1 mole unless they tell us otherwise. So now they're telling us that each particle represents 0.02 moles. So part A, determine the molarity of Q2, Z2, and QZ at equilibrium. Okay, so molarity is moles over liters. So we are figuring out the molarity at equilibrium. Now this says that the diagram shows at equilibrium. So this particle diagram is at equilibrium. That's what the problem tells us. So here's what we can do to find the molarity. I'll do it over here off to the side. So the molarity of Q2. All right, so I'll do brackets Q2. We're going to count. Now, they didn't tell us whether the red or the blue was Q2. It doesn't actually matter. Here's why. I'm going to count them. So I'm going to say that the blue ones are Q2. 1, 2, 3, 4. Well, let's look at the red ones. 1, 2, 3, 4. So there are actually equal amounts of Q2 and Z2. So there are 4 particles. I need moles over liters. So for molarity, this is going back to particle diagrams. Counting is really important. So there are 4 particles of Q2. 4 particles. Now, the problem tells us that each particle is not 1 mole. It tells us that each particle is 0.02 moles. Now, could you do this without showing the work I'm about to show? Yeah, you could. I'm just showing you so you know how we get what we get. So here's what I'm doing. 4 particles. Each particle represents 0.02 moles. So if there are 4 particles of Q2, represents 0.08 moles. Now, could you just do 4 times 0.02? Yes. So the reason that it's 0.08 moles is because they tell us here each particle represents 0.02 moles. So 0.08 moles over 2 liters of solution. We get 0.04 molar. There's Q2. So then we need Z2 and we need QZ. We're trying to find the molarity of all 3. So if I said that the blue was Q2, the red will be Z2. There's also 4 particles. There's also 4 particles, so there's the same number of moles of Z2 in the same size container. So the concentration, the molarity of Q2 and Z2 are actually the same. .04 molar. Then if we look at QZ, we've got 1, 2, 3. I just like marking them differently so that as I'm counting them, it's easy for me to kind of see how I'm counting them. You count them how you count them, but remember particle diagrams is about counting. So here I have 3 particles of QZ. Remember that each particle is 0.02 moles. So there's 0.06 moles of QZ in a 2-liter container. Moles over liters is molarity. So QZ is 0.03 molar. Now, what if they didn't tell us that each particle was 0.02 moles? They didn't tell us that each particle was 0.02 moles. We just assume it's 1. And it would be 4 moles over 2 liters, 4 moles over 2 liters, 3 moles over 2 liters. But they told us to have each particle represent something different. So that's the molarity at equilibrium. Just counting. Now B, write the equilibrium constant expression in terms of molarity and calculate the equilibrium constant. This is very much a type of question that you could see, whether it's free response or whether they made it into multiple choice. So equilibrium constant expression in terms of molarity. Which K is that? It's in terms of molarity. C. Molarity is concentration. So we're writing the Kc expression. Here's our balanced equation. All right, if they all have concentrations, we're assuming they're aqueous or they're gases. So we write our equilibrium constant expression. Don't forget exponents. So Kc, concentration of Qz squared over Q2 times Z2. Then it says calculate the equilibrium constant. That's what this was for. These are the concentrations at equilibrium. These are the concentrations that get plugged into K. Because we are at equilibrium. If we weren't at equilibrium, we wouldn't be calculating Kc, we'd be calculating Qc. But because we know that we're at equilibrium, plug everything in. So you get 0.03 squared over 0.04 times 0.04. Assuming I plug this into my calculator correctly, I got 0.56. So here's our Kc value. Our equilibrium constant. Remember, your equilibrium constant tells you what you have more of at equilibrium. So since K is less than 1, that means that we have more reactants at equilibrium than products. So again, that's just looking at another particle diagram question where we have to count the particles in the particle diagram and apply it to things that we've looked at before. Any questions on example 25? All right, if not, we're going to flip back to LeChatelier's principle. So the first LeChatelier's principle example we're actually going to do is example 18. But I want to talk a little bit about LeChatelier's principle first. So you have this diagram in your notes. And LeChatelier's principle is about how a reaction will respond when you change its equilibrium. You stress its equilibrium. So how will the reaction respond when you do something to it? Now with LeChatelier's principle, this might not be the best analogy, but it helps. Think about LeChatelier's principle like a seesaw, right? Like a teeter-totter. So at equilibrium, we have equal rates. Now the concentrations aren't equal, but the rates are equal, so we're going to say it's balanced. If you make a change to either the reactants or the products, you're going to cause it to be off balance. Right? One way or another, it's going to become off balanced. Well, the reaction is going to respond. So we call this a shift. It's going to respond in a way, it's either going to make more reactants or it's going to make more products. Those are your two options. It's either going to shift right to make products or left to make reactants. And so it's going to shift in a way that brings it back to equilibrium. Now, we can also relate this to Q versus K. And we will look at some examples where the question actually says justify using Q versus K. So instead of just saying, well, you're adding reactants, so it's going to shift this way, or you're adding products, it's going to shift this way, we can also relate it to Q versus K. And they've started asking more and more questions where you're talking about how changing the equilibrium changes K. Because remember, when you make a change, K is a constant. The only thing that changes K is temperature, because that changes the rate constant. So the system's going to respond. You might change concentration, you might change pressure, you might change temperature. And temperature is unique because temperature is based on whether the reaction is exothermic or endothermic. If it's exothermic, it's going to shift a certain way. If it's endothermic, it'll shift another way. And then we'll also look at how exo and endothermic affect the equilibrium constant. Now, there was another question on the graph that was in the notes. So we looked at equilibrium graphically. So I'm going to ignore anything from this dotted line over for now. Notice each of the lines remains constant. That tells us that it's at equilibrium. Well, what happens when we're looking at LeChatelier's principle, or we're thinking about this stress of equilibrium, is we do something to it. So here's the stress. You have this sharp increase in SCN minus. It doesn't matter what your reactants and your products are. Right here, though, we see there's this stress. We see this sharp increase. Well, that means that all of a sudden we added SCN minus. This was at equilibrium. Concentrations were remaining constant, and then we did something to it. Well, then this highlighted part, this is how the system is responding. When it's responding, that's like it's shifting. Like there are different words for it balancing back out. And so if you add SCN minus, you'll notice that SCN minus and Fe3 plus decrease. FeSCN2 plus increases. So it's shifting in a way that you're trying to undo that stress that was done. And if you notice, right, we didn't completely undo it because we had a little bit more SCN minus than we did initially, but notice it gets back to equilibrium. So it was at equilibrium, we made a stress to it, we made some change, the reaction responded and got back to equilibrium. So this stress is where you're changing Q. You're changing Q, and the reaction is going to respond in a way that gets Q back equal to K. Now, when we think about the value of the equilibrium constant, right, the value of the equilibrium constant changes when temperature changes. That's it. The only time K changes is when temperature changes. But exo and endothermic reactions are different. So if it's endothermic, when you increase temperature, you're increasing K. If it's exothermic, you increase temperature, you decrease K. And so exo-endo thermicity is actually going to affect how K. So endothermic, increased temp, higher K. Exothermic, increased temp, lower K. So what we're going to do is we're going to look at some of these examples. We're going to actually start with example 18. So we're skipping 17 for now. We might come back to 17, but I want to make sure that we have some time, and I want to focus on some of these examples that are in mastering. So example 18 is on page 15. This is like number 27 on mastering. All right, this is like number 27 on mastering. So example 18 says, consider the following equilibrium for which delta H is less than 0. Right, so before I worry about anything else, this is important. Delta H is less than 0. You have a negative delta H. That's telling us whether it's exo or endothermic. Delta H is less than 0. You have a negative delta H. That's telling us that this is an exothermic process. Now, I always recommend thinking about heat, right? Because exo-endothermic is whether heat is absorbed or released. Think about heat as being added to the reactants or the products. So if it's exothermic, heat exits the system. Heat is released. So heat you can think about as a product. If heat is released, we think about it as a product. Writing heat in here can help because as we change temperature, we can think about adding or removing heat. Now, let's look at part A. So how will each of the following changes affect an equilibrium mixture of the three gases? So for A, if O2 is added to the system, right, so here's what I'm going to draw an arrow above O2. So here's going back to, right, here's our balance, right, our seesaw. You're adding more O2. So now we have too many reactants compared to products. Right, you have too many reactants compared to products. You need to get equilibrium back to where we have the correct ratio. So if you have too many reactants, we need to use up the reactants, make more products to get back to equilibrium. So if O2 is added to the system, this is what we would say. We said we want to make more products. And if we want to make more products, we need to use up the reactants to make more products. So if O2 is added to the system, we would say that it shifts right. What that means is we have reactants forming products. So if it shifts right, your products are on the right. You're making more products. So we could say there is more O2 than required for equilibrium. All right, so that extra O2 needs to be used up. Let me put that here. Extra O2 needs used up. I'm going to change because the green's hard to see. So since you have too much oxygen, the reaction is going to shift in a way that's going to reduce the oxygen back down, which means you're also using up SO2, and you're creating more SO3. Now for part B, the reaction mixture is heated. Well, if it's heated, that means that you're adding heat. This is why thinking about heat as a reactant or a product is useful. So here are your reactants and your products. It's at equilibrium. If you heat this reaction mixture, well, you're adding more to the product side. The ratio is off. So the reaction is going to respond in a way that brings it back to equilibrium. And so if you have too many products, you need to use up your products and create more reactants. And so for this one, we'll say shifts left. All right, it's going to shift left because now we have too many products. So now it's going to shift to use up the products and create more reactants. It needs to get that ratio back to where it was. So I'll say heat is a product because it's exothermic. So adding heat is like adding a product. All right, so the reaction is going to shift in a way that uses up whatever was added. Now part C, this is one that you might look and you're like, okay, well, how is this going to affect equilibrium? Well, the volume of the reaction vessel is doubled. So if you are doubling the size of the container, so you're going from maybe a smaller container to a big container. When you double the volume, so you go from this volume to this volume, what are you doing to the number of collisions inside the container if you make the container bigger? You're decreasing them. Equilibrium, right, wants a certain pressure. So if you're decreasing the pressure, the reaction needs to shift in a way that brings the pressure back up. So if you are decreasing the pressure, it's going to shift to the side that has more moles of gas. So if you look here, you have 3 moles of gas. Here you have 2 moles of gas. So it's going to actually shift left. I'll start answering part C down here. So we're going to say shifts left. So I'm going to say increasing volume decreases pressure. That's what we just said. Increasing the volume decreases the pressure. So the reaction will shift to bring pressure back up. And we'll say, so it favors side with more moles of gas. The side with more moles of gas is the left side. So the whole point of LeChatelier's principle is that whatever stress we're putting on the system when it's at equilibrium, the reaction is going to shift in a way to try to undo that change as much as it can. Part D, a catalyst is added to the mixture. What's the purpose of a catalyst? It really has one purpose.
Reduces the activation energy.
Right, reduces the activation energy, right? Speeds up the reaction. Doesn't do anything with equilibrium. So for part D, we're going to write no effect. Right. A catalyst only speeds up a reaction. It has nothing to do with equilibrium. So you add a catalyst, right? Once this is at equilibrium, we're talking about adding a catalyst to the mixture once it's at equilibrium. If you add a catalyst at the beginning, yes, it's going to speed it up. But once it's at equilibrium, if you add a catalyst, nothing's going to happen. So then E, the total pressure of the system is increased by adding a noble gas. Now this is a little tricky, but this one's also no effect. Because it's a noble gas. Noble gases are inert. Noble gases do not react. So this is going to be no effect. And then finally F. SO3 is removed from the system. So now I'm going to erase these arrows so that I can look at it separately. So SO3 is removed from the system. So I'm going to take SO3 away. So now let's think about it this way. Here's my equilibrium. I'm going to remove some SO3. I'm going to remove some product. So we still have disrupted the ratio at equilibrium. So if we've removed some SO3, we've taken some away, the reaction needs to shift in a way that's going to make more of what we took away. So if it needs to make more of what we took away, we would say it shifts right. So we'll say shifts right. If we don't have enough products. So the reaction is going to shift in a way to create more products. So you just have to think about how does the reaction have to shift in order to get back to equilibrium, to get back to the ratio that it was at. Any questions on this one before we look at 19? Okay, so 19. So 19 is a little bit different because it says, how do the following changes affect the value of the equilibrium constant for an exothermic reaction? All right, so we don't care about shifting, right? We just want to know how's it going to change the equilibrium constant. So here's what I always recommend, because this could very much be a multiple choice question. Right? Which of the following effects? Or circle all that apply, right? Something like that. Here's what I recommend doing before you look at anything else. Okay, we want equilibrium constant. So I'm just going to write K. Exothermic reaction. So I'm going to say heat is released. And I'm just going to write information down that I know. Right, how do the following changes affect the value of the equilibrium constant? I'm going to write down that I know temperature affects K. So that might help. So, for example, 19. A, you remove a reactant or a product. How does it affect K? It doesn't. You remove a reactant or a product, you're not changing K, you're changing Q. The only thing that affects K is temperature. So, part B, you decrease the volume. Again, no effect on K. You decrease the volume, you change Q. Now, temperature. This will affect K. So with temperature, it's an exothermic reaction. It's important that we know whether it's exo or endothermic. Here's how temperature affects K. If it's exothermic, It's an inverse relationship. If it's endothermic, it's a direct relationship. So direct meaning you increase temperature, you increase K. Inverse, you increase temperature, you decrease K. So if it's exothermic, right, we know it's exothermic, so it's an inverse relationship. So you decrease temperature. That means that you are increasing KEQ. So you're going to increase your value of your equilibrium constant. And then addition of a catalyst, again, no effect. A catalyst affects the speed that we reach equilibrium, but it doesn't affect equilibrium itself. Right? It doesn't affect the equilibrium constant. So from this is the most important, knowing how K is affected by temperature. Exothermic, it's inverse. Endothermic, it's direct. Questions on this example? Oh, and that was like 28 on mastering. That was like number 28 on mastering. 2-8. All right, so then example 20, this is another one where we're just looking at kind of putting them together. So here's what I want you to do is see if you can see how the reaction shifts. So for reaction shifts, you really just need to say, does it shift right or does it shift left? Now, if it helps you to say reactants or products, that's fine. Just know that reactant, if it makes more reactants, it shifts left. Makes more products, it shifts right. So see if you can go through, right? If you need to erase and change it when we go through it, that's okay. I want you to just focus on the reaction shifts. So see if you can fill in the reaction shifts column. So here's how you're changing. Here's your equilibrium with your delta H. So see if you can fill that in. All right, so I'm kind of going up here as you guys are filling it in. So as I'm going through, if you want to check, you can. But I'm going to keep going through. I'm kind of writing some information over to the side as well. So I have the reaction shifts column. If you want to check, you should have right, no shift, because argon is an inert gas. So noble gas doesn't react. If you also look, it's not part of the Q expression. So you're going to have no shift for adding argon. When you decrease the pressure, it's going to shift right. Because if you're decreasing the pressure, in order to get back to equilibrium, you need to bring the pressure back up. So it's going to shift to the side with more moles of gas. That's the right side. When you increase the temperature, it's going to shift right because it's endothermic. So heat acts as a reactant. Adding a catalyst will have no effect on the shift. And then decreasing the volume of the container. So if you decrease the volume, you're increasing pressure. So to get back to equilibrium, you need to bring pressure back down, which means you shift to the side with the least number of moles of gas, which is the left side. Now, for change in K. And for change in K, remember the only thing that can affect K is temperature. So here's what I'm going to write for the first 4. Okay, the change in K, none. Add PCl5, remove Cl2, add argon, decrease pressure. None of those affect the equilibrium constant. You're affecting Q, not K. Now, when you increase temperature, this is an endothermic reaction. Endothermic has a direct relationship between temperature and K. So you increase temperature, you increase the value of K. And then for catalyst and changing volume, those also don't have any effect. Temperature is the only thing that will affect your value of K. That's it. So this was combining the way that the reaction shifts. So you're looking at, are you creating more products or more reactants? And then also how it changes K. Any questions on that? We have two more that are kind of practice AP style free response questions. They're short though. They're examples 21 and 22. Any examples? Any questions on this? So let's just at least get started on example 21. So again, these are similar to parts of free response questions where it asks you to use Q as a justification. So for example 21, it gives us this equilibrium of SO2 and O2, and it gives us the Kp expression. Now A says, a reaction vessel contains a mixture at equilibrium. So you have something at equilibrium. Then it says a valve is opened to allow SO3 to enter the vessel. So again, before I read on, a valve is open. So once we are at equilibrium, right, everything is balanced. Then when we're at equilibrium, we're allowing a stress to happen. We're allowing SO3 to enter the container. Will the partial pressure of oxygen increase or decrease in response? Justify your answer using the reaction quotient Q. So we have to justify our answer using Q. When you're answering questions like this, first, make sure you're actually answering the question. Now, here's what I would suggest doing. Even if you don't know the answer right away, start by saying, partial pressure of O2 will, and leave yourself space. All right, partial pressure of O2 will blank. Because that's how College Board wants you to start your answer. It's either going to increase or decrease. So you're leaving yourself that space, and then you can start working through your thoughts. Well, if I increase the amount of SO3, equilibrium has been disturbed. How will the system respond to adding SO3? It's to use up that SO3 to get back to equilibrium. So here's kind of what I'm going to go through and say. Oh, this is dead. Okay. All my markers are dead. When SO3 enters the system, partial pressure of SO3 increases. That's just what's happening. Now, let's think about this because it wants us to justify in terms of Q versus K. Well, if you are increasing the pressure of SO3, you are increasing the amount in the numerator. You're increasing K. So if it was at equilibrium, Q was equal to K. Now you've increased K. So now Q is greater than K. So if Q is now greater than K, the reaction is going to shift in a way that makes Q equal to K again. So I will say the reaction will shift to use excess SO3 and form more reactant until Q equals K. So let's think about what we said now, because we have to actually answer the question. So if the reaction will shift to use up excess SO3, it's going to use this up. Well, it's going to shift in a way to create more reactants. So if we're creating more reactants, we're increasing the amount of O2. I'm going to fill in that it will increase. Okay, so I'm going to read through this again, and then we'll go through part B. So in part A and really in part B too. This is just saying you have something in equilibrium and you are disrupting equilibrium. You're putting a stress on equilibrium. And then it wants you to answer what's going to happen. Are you going to increase or are you going to decrease, in this case, oxygen? Now, it specifically says justify your answer using Q. So we can't just say, based on LeChatelier's principle, if we increase SO3, we're going to end up needing more reactants. It specifically wants Q. So we have to think about how at equilibrium, these are equal. That's the definition of equilibrium, when Q is equal to K. Well, if we're disrupting, we're thinking about how is that going to change the value of Q. It doesn't have to put it, you don't have to put in numbers. You're just comparing the two values. Q will be greater than K. So to get Q back down equal to K, it's going to shift toward the reactants. So you're going to produce more reactants, use up more product to bring the ratio back to equilibrium. So for part B, a reaction vessel contains the mixture, so it's the same initial setup. A valve is opened to allow SO2 to enter the vessel. So now instead of SO3, now we have this system at equilibrium. And after it's already at equilibrium, we're increasing the amount of SO2. We're adding more SO2 to this system that's already at equilibrium. Now it's the same question. Will the partial pressure of oxygen increase or decrease in response? Justify your answer using Q. So let's start the same way. Pressure of O2 will blank. You always want to answer the question that they are asking first, then provide your justification. Make it easy for those that are grading the AP exam. Make it easy for them to find your answer. So pressure of O2 will blank. And so now we're going to go through, we're going to start our justification. So I'm going to start it in a similar way. When SO2 enters the system, pressure of SO2 increases. That looks like an 80, that's an S. So when SO2 enters the system, the pressure of SO2 increases. That's just what is happening when the valve opens. Now let's think about what that does to Q. You're increasing only the amount of SO2 right away. Right away, all you're adding is SO2. Well, now you're adding more to the denominator. You add more to the denominator, you're making Q small. So now Q is less than K. Right, there is not enough, if we do this, right, Q, K, there's not enough product relative to how much reactant we have now. So if Q is less than K, I can draw this and say reaction will shift to consume excess reactant. So we have to use up that extra reactant that we've added and form product until Q equals K. So our justification using Q, it's just looking at this, whether Q is greater than, equal to, or less than K. So if it's going to consume excess reactant and form more product, the arrow is going to look like this. Well, if we have to consume SO2, so that's what we added, we also are using up oxygen because it's a reactant. And we're forming more SO3. So the pressure of O2 will decrease. Because to use up that extra SO2, we also need to use up oxygen to create SO3. So we're talking about what's going to happen to the pressure by comparing Q versus K. These are actually sample free response questions that College Board has released. So you're still thinking about how it shifts, but then we're going to compare Q to K. So the last example is example 22. All right, the last example is example 22. And they give us a reaction up at the top. And the first thing it says to do, part A, write the equilibrium constant expression Kc. So go ahead and write the equilibrium constant expression. You can answer part A. Pay attention to states of matter. But write the equilibrium constant expression. Once Kc. Remember, water's a liquid. Liquids do not get included. Right? No liquids in the equilibrium constant expression. So we have H3O plus times F minus over HF. Now part B, a small amount of solid sodium fluoride is added. Right, so a small amount of solid sodium fluoride is added to this container. So these are all aqueous solutions, water's a liquid. Will the concentration of hydrofluoric acid, HF, increase or decrease in response to the stress? Justify your answer using Q. Now this is a little bit tricky. Because a lot of times you look at this initially, you're like, well, NaF, that's not in here. Right, it's a solid, it's not in the equilibrium constant expression. So let's start by giving like our outline, right? At once, will the concentration of HF increase or decrease? So I'm going to start by saying concentration of HF will blank. Give myself space to answer the question once I've justified. So, something to think about. NaF has sodium in it. Any solid with sodium is soluble. So I'm going to say NaF is soluble and it will dissociate to form Na plus and F minus. The reason that matters is because this is all in water. Right? This is all in water. No water is not included in here. But these are all aqueous solutions. They're all dissolved in water. So if I put NaF into this mixture, it's going to dissolve in water if it can. So NaF is soluble. It will dissociate to form Na plus and F minus. So here's the biggest thing, right? F minus. So when the concentration of F minus increases, think about Q. It's the same thing, but I'm just focusing on Q now. If I'm increasing the amount of F minus, I'm increasing the amount of what's on my numerator. I'm increasing the value of Q. So when concentration of F minus increases, Q becomes greater than K. So now we have too much product compared to reactants. So reaction will shift to form HF and use, nope. Okay. It'll form more HF and use up H3O plus and F minus. All right, and it will do that. I guess I can continue here until Q equals K. So because we're adding NaF, we're actually adding F minus. When we add F minus to the system that's already at equilibrium, Q is now greater than K. You've added more into the numerator. Q is now too big. So to get Q back equal to K, we need to create more reactants. So if we're creating more reactants, we're shifting left, the concentration of HF will increase. So we're still thinking about LeChatelier's principle, but we're tying it into Q as well. So then the very last part, part C, the solution is diluted to twice its volume. Right, so let's think about what that means when dilution. All right, so instead of 1 liter container, I'm just using numbers. Instead of a 1 liter container, we have a 2 liter container. So let's say instead of a 1 molar solution, right, 1 mole over 1 liter, you now have 1 mole in 2 liters. So when you dilute a solution to twice its volume, the molarity is actually cut in half. So when you dilute a solution to twice its volume, you're actually cutting the molarity in half. Because now you're dividing by a number that's twice as big. So then for part 1, what's the mathematical relationship between Q and K as a result of this stress? So if we look at this, Q, all right, here's KC, QC, I just said the molarity gets cut in half. So that means that we have 1/2 of H3O plus times 1/2 concentration of F minus over 1/2 times the concentration of HF. All of those numbers get cut in half. When you dilute to twice the volume, each of those molarities are getting cut in half. Well, if we look at this, that's just 1/2 times Kc. Right, mathematical relationship is just an expression. Here's that expression. When you are affecting molarity, you are affecting Q. Since we're cutting the molarity in half, that means that Q is actually equal to half the value of K, since you're cutting all of the concentrations in half. And then number 2, will the concentration of fluoride ion increase or decrease in response to the stress? Justify your answer using Q. Okay, so right here we said Q is half of K. So Q is half of K. Q is less than K. So since Q is half of K, Q is less than K, the reaction has to shift in a way to get Q back equal to K. The point of equilibrium is that our mixtures, our reactions are shifting in a way that will get it back to equilibrium. So concentration of F minus will, I'm going to leave that blank. I'll answer that once I justify. So Q is less than K. All right, we know that from part 1. So reaction will shift to create more products until Q equals K. Since Q is less than K, the reaction will shift to create more products until Q equals K. So if it's creating more products, F minus will increase. Right, concentration of the fluoride ion will increase.